Hello, I'm Shaumik and I'll be presenting the preliminary results of our work, Retrospective Motion Correction of MR Images using Prior Assisted Deep Learning. One of the most common causes of artifacts in MR imaging is the patient motion. The physiological motion, such as respiratory movement, can be tackled by specific sequence design. But in this work, we are trying to address the problem of physical movement of the patient, which is less predictable in nature and can be both voluntary or involuntary, such as in the case of patients with Parkinson's disease. In this work, we have used T1, T2, and proton density weighted images from the ICSI dataset. 100 subjects were chosen randomly for each train, test, and validation set. T1 and proton density weighted images were co-registered with the T2 weighted images. Then the T2 weighted images were artificially corrupted to simulate motion using a modified version of the random motion transformation of TORCH-IO, with a rotation between negative and positive 1.75 degrees. Two different types of image priors were explored during this work. The first is using similar slices of the same contrast but from different subjects which were not corrupted by motion. And in the second set of experiments, we've used different contrasts from the same subject without any motion corruption as our prior. We have used two different models in our work, UNet and MR Reconstruction ResNet. For supplying the image priors to the network, we experimented with two different approaches. In our first approach, we concatenated the prior images along with the corrupted image on the channel dimension and supplied them all together as multi-channel. For our second approach, we created dual branch version of the networks as can be seen on the right. The corrupted images were provided to the first branch of the networks. The prior images were concatenated together on the channel dimension and were supplied to the second auxiliary branch. Both branches meet at the latent space while creating two different latent representations. We also experimented with two different ways of combining those two latent representations. For the first method, we simply added them together to obtain the final latent space. For the second method, we supplied both the representations to a convolution layer with a kernel size of 1, which provided a final combined latent space as output. Now let's have a look at the results. The quantitative analysis was performed with the help of structural similarity or SSIM. The leftmost violin plot shows the SSIM of the corrupted input image while being compared against the ground truth. The second set of violin plots shows the output of the model without supplying any kind of priors, also known as the baselines. The third set shows the results of the models which received different contrasts from the same subject as priors. And finally, the rightmost set shows the results for the models with 10 similar slices as priors. It can be observed that by supplying different contrasts from the same subject as prior to the networks, the performance of the models improved significantly. For ResNet, multi-channel and both the dual branch models have shown similar improvements over the baselines, and further experiments have to be performed to determine the winner. However, for UNet, only the multi-channel version has shown any improvement over the baselines, and the dual branch versions didn't show any. Now when it comes to supplying 10 similar slices as prior, none of the models have shown any improvements over the baselines. Let's have a look at the results visually, though it might be difficult to detect the differences here. By looking at the images more closely, it can be said that the qualitative analysis confirms the findings of the quantitative analysis. Now to conclude, we have presented here our initial experiments which have shown promising results for the different contrasts as priors, but not so promising results for 10 similar slices. In future, we will try to determine the reasons and the possible solutions of the failures. The clinical applicability of these methods will also be tested. Thank you so much for your attention.